previous video, we defined what a vector and a scalar is. We also went through examples of each, and we ended off the video by going through vector notation. Now in this video, we're going to look at vectors in a bit more detail, and we're going to start with the graphical representation of our vectors. Now, as you can see, we have a few arrows pointing in different directions. Now, doesn't this remind us of what the definition of a vector actually is? Let's recall that first. So we know now that a vector is a physical quantity consisting of both magnitude and direction. Now, when dealing with the graphical representation of vectors, this is really what each arrow represents. So we have a dot here on the end, which represents our tail, so really where the vector begins. And then we have the body of the arrow here, which represents our magnitude. And we have our arrow pointing in the direction of where this vector is. We know by now that directions are a huge part of the properties of a vector. And so there are three different methods here on the screen that we could use to represent the direction of a vector. The first way is what we call relative direction. So that means left or right, up or down, forward or backward. So for example, the gravitational acceleration. And we know that the gravitational acceleration is equal to 9.8 meters per second squared. And in the last video, we did speak about this, where we said that it actually acts downwards. So this is the reason you're sitting on your seat at the moment with maybe a bit of willpower. So that would be an example of relative direction. Now let's move over to compass directions. We all have an idea of what a compass is, as well as where everything is. So everything as in north, east, south, and west. So we could also use these compass directions to help us express the direction of our vector. So for example, if our direction is pointing upwards, then we could say it's pointing north. Similarly, if downwards, we can say it's south. But sometimes our vector may fall in between two compass directions, and there we could maybe say northeast, or we could say east of north, or we could even use an angle. So let's say we have this vector here, and it is looking like it is pointing approximately 45 degrees to the horizontal. But now if we were to use compass directions to express this, we could say either 45 degrees north of east, or since it's halfway exactly, we could also say east of north. And then lastly, we can use bearing as one of our other methods to express our direction. So with bearing, this speaks of direction relative to a fixed point, which is usually north. So, or it's usually with respect to north. So with this vector here on the screen, we would say that it is a certain degree or certain angle from north in a clockwise direction. So we can say that this vector is perhaps 115 degrees in a clockwise direction with respect to north. We should now be able to draw vectors. Let's have a look at this question on the screen here. So it says that we need to draw the following vector quantity where we have velocity equal to 8 meters per second east. So here we can see this is indeed a vector because it has magnitude as well as direction. So we can break this down into 4 steps, and our first step would be to write our scale down. Now I don't know if any of you remember back to when you took technology as a subject, you would draw buildings and objects, real life objects, with the use of a scale. So of course we cannot represent a real life sized building on paper, we would have to actually scale it down to fit. So the same thing goes for our vector, and when we are trying to draw our vectors, we have to decide on a scale. So you can be flexible in this. We only have 8 meters per second as our magnitude. So we could maybe say that 1 centimeter represents 2 meters per second. But like I said, 8 meters per second is not too big of a magnitude to represent. We could make it 8 centimeters, so as in 1 centimeter representing 1 meters per second, but I'm just going to use 2 meters per second instead. Now for our second step, we want to choose a reference direction. So since we have east here, maybe we'll choose the compass and say that north will point up the page. Now the third thing that we'd want to do is to actually determine what the length of our vector would be according to our scale. So if we are trying to represent 8 meters per second and we have a scale where 1 centimeter is meant to represent 2 meters per second, we can say that x now will be equal to 4 centimeters. And by the way, your teacher will measure your final vector to see whether it goes according to your scale and actually represents its magnitude. Now lastly, we can get to actually drawing the vector quantity, and I've included my ruler here in the corner. So our vector will be, or should be, 4 centimeters long, of course with our tail indicating that our vector is starting, and with our arrow indicating that it's ending, and also pointing in the direction of east. Now it's very important for us to realize that vectors have what we call mathematical properties, and we can see that when we're dealing with more than one vector at a time. So in this case, we can see that we have 2 arrows here, 2 vectors in other words, and they are the same length, so meaning that they're the same magnitude, and they're also pointing upwards in the same direction. So that means that we can say that these 2 vectors are equal. Now we can only say that because they are equal in magnitude, or well, they have the same magnitude as well as the same direction. So now in this case over here, we wouldn't say that these 2 vectors are equal because the one is pointing upwards and the other is pointing downwards. But we can say, since they are the same, they have the same length, we can say that they are equal in magnitude. Now if you remember back to our vector notation, we can represent the magnitude of a vector by simply leaving out the arrow. So using vector notation, we can tell our marker that in this case over here, where we have 2 vectors with the same magnitude, however not the same direction, we can say that the magnitude of force 3 is equal to the magnitude of force 4 by leaving out the arrows, and your marker will know exactly what you're referring to. And when we have to consider vectors in 2 different directions along one dimension, so either up or down or left and right, we would have to choose a positive reference direction. So in this case, maybe we could say we'll choose upwards as positive, meaning that our 4th force over here, force 4, would then be called a negative vector. So when we say that a vector is negative, it simply means that it is pointing in the opposite direction from what we chose as positive. Now that we know that vectors have mathematical properties, we should not be shocked when we see a negative vector or a positive vector. Remember that a negative vector simply means that the vector's direction is in the opposite direction from what our positive reference direction is. So with that being said, we need to remember to choose a positive reference direction whenever dealing with vectors. We are now led to the next two terms on the screen here, and the first being our resultant vector, which is defined as a single vector whose effect is the same as individual vectors acting together. You would also see that some textbooks call it the algebraic sum of all the vectors. We then get introduced to this term here called the equilibrant, and it is defined as the vector which has the same magnitude but opposite direction to the resultant vector which we defined just now. We can use this next scenario to really illustrate the concept of resultant vectors. So we can see here that we have a block, and let us imagine that we have two friends and they are each pulling or pushing with a specific force. Now, to make this easier for ourselves, we can represent these forces as a resultant vector, which remember is defined as a single vector whose effect is the same as, now in this case, these two forces acting together on this object here. So what we'd want to do is first choose our positive reference direction, and since these forces are both going to the right, I'll just choose right as positive. So since the resultant vector is also referred to as the algebraic sum of two or more vectors, we can then say that our resultant vector is equal to force of F1 plus the force of F2. And remember, the arrows are indicating that these are vectors, so we need to take their directions into consideration, which is exactly why I first said what my positive reference direction was. So therefore, we would substitute a positive 8 for force 1 and a positive 12 for force 2, which will leave us with 20 newtons and then to the right. But now let's look at a different scenario where we can actually see here that our second force of 12 newtons is actually now being applied in the opposite direction from what we chose as positive. So now our resultant vector will actually change. So if we were to set up our vector sum, it would look something like this. But the difference here is that we have to remember to take the directions into consideration with regards to our positive reference direction. So in the last case, we substituted both positive values, so positive values for our second force as well as our first, but now in this case our second force is going in the opposite direction. And remember, in our previous slide we saw that negative vectors indicate that that vector is going in the opposite direction. So that means that we would now substitute a negative 12 in the place of F2, which if we do the math here, we will see that we have 8 minus 12, because a positive times a negative gives us an overall negative, leaving us with a negative 4. But now we don't really want to leave our final answer in this way. We want to really conclude nicely what our resultant vector is in this case. So since it's a negative 4, that simply means that it is 4 newtons to the left. So what we've really done is swap out all the vectors in each case for each block and represented it as a single vector, which is exactly what a resultant vector is all about. And so you've guessed it, these yellow arrows here would be our equilibrants for each of these scenarios. And here we can see that in both cases, each of them are equal in magnitude to their resultants, and they are in the opposite direction. So what we actually did just now is add vectors using one of our techniques, and that is algebraically, so using mathematics and algebra concepts. Now we can also determine the resultant vector in this case graphically using the head to tail method. Now, this should actually take you back to our first slide where we went through the graphical representation of vectors, because it is important that these vectors are actually drawn to scale so that we can get to the correct length of our resultant vector and therefore the correct magnitude. So what the head to tail method tells us, or it goes as follows: we have to first arrange our vectors from head to tail. So as you can see here, we have the head of our first vector going to the right that way, and then just below it we put the tail where the head of the previous one was. And so to find our resultant vector, we can then say that our resultant vector will go from the tail of the first vector to the head of the last. So it's actually opposite. So if we were to draw that, it would look something like this. And if someone were to measure that according to your scale, it should actually make sense and come to 4 newtons. So if you maybe use the scale of 1 centimeter representing 2 newtons, this length should be 2 centimeters representing 4 newtons, which is pointing to the left. So I don't know if you noticed, but these are our same forces from this scenario here where we determined the resultant force algebraically. We got to the same resultant force graphically. So force 1 was going to the right, force 2 was going to the left, and so we know that our resultant force goes to the left. So remember, when you're trying to determine your resultant vector graphically, it needs to go from the tail of the first to the head of the last so that you get the correct direction of your resultant vector.